So most of you know me. I'm Stephen Johnson. So I'm in MIT Applied Math. I'm also affiliated with MIT Physics. And I'm not going to give a technical talk today. I'm just going to give an overview, a little bit of a historical overview of Meep and try and explain where it fits into the larger pantheon of computational electromagnetism. So Meep has been around for a while. It's been supported by a large number of groups. So I'm at MIT. I'm also affiliated with the MIT Institute for Soldier Nanotechnologies, which helped us get funding for this through the Army. There's also funding, was early funding through NSF. There's funding from Google for test programs. There's some funding from the Simons Foundation. There was some funding from a company called Computations that Artavan was running for a while. So as you know, so Meep is one of our free electromagnetic simulation packages. It originally stood for MIT electromagnetic equation propagation, but I think John Giannopoulos suggested an alternative meaning of Maxwell's equations for every person that I quite like. So this is an FDTD Maxwell solver. It's gotten to be quite general and powerful at this point. It has several thousand citations and has quite a few contributors, as I'll explain. You may notice the logo, which I created in 2003 or 2004. So if you look closely, the time shown on this clock, which stands for time domain, and there's a grid there, is 8:18. And the reason for that is that at MIT, everything has a number. So the physics department is course 8, and the math department is course 18. And of course, this is when Meep was created. Actually, I was in several of the people were in the physics department, and then I subsequently joined the math department in 2004. So Meep started out in 2003. It was actually a project started by David Roundy, who was then an MIT postdoc, shown here, wearing his lumberjack attire, and he's currently a professor of physics at Oregon State. So some of you may know him from he developed a version control package called DARCS, which was actually a distributed version control that actually predated Git, I believe. Had some interesting math behind it. And so he actually started this out as a supplement to our crusty old Fortran FGTD code that we've been using in John Giannopoulos' group for quite some time. So he was a postdoc with John Giannopoulos. In the initial version, if you look at the very first check-in on Git, it actually only supported cylindrical coordinates because we didn't have any code for simulations in cylindrical coordinates, and we were doing a bunch of things with fibers and stuff at that time. And it was called Dactyl for just two fingers, so for 2 dimensions, and it was only C++. So to control it, you had to write a C++ program for every simulation. So he was very early on. He was collaborating with Mihai Bănescu and Peter Bernal at MIT, who added 2D and 3D support. And later in the same year, I joined, and I quickly added a scripting interface in Scheme, not in Python, based on the interface from my MPB eigensolver, which had started several years earlier and used Guile scripting, which is a Scheme dialect. And in 2004, I joined the faculty, and I had a brand new graduate student, Artavan Eskui, who joined my group, and he started working on Meep on subpixel material averaging, which greatly improved the accuracy. And the unifying philosophy of Meep, which is kind of exemplified by the subpixel material averaging, but not limited to it, is pervasive interpolation. That everywhere in the interface, you're provided the illusion that you have continuous coordinates in space. You can specify an object or a current source or an output any place you want, and under the hood, it will interpolate, so that if you continuously change the inputs to the program, the output should change continuously. So this continued on for a number of years. It actually wasn't until 2017 that we integrated Python scripting with the help of a guy named Chris Hogan, who was hired by Artavan's company of Computations with some funding from NSF and others. And there was actually an earlier Python API in 2010 developed by Peter Beensman's group at Ghent, but it was never really fully integrated. It was a separate add-on that you know, with the in order to get the full power of Meep, we needed to actually change the internal C++ code to make it hook more deeply into Python and expose some more functionality. And then more recently, you heard some talks yesterday, and it'll be also talk today about inverse design. So this was prototyped initially by Homer Reed in 2019, and it was really brought to a working state by Alec Hammond starting in about 2020. So if you look at this is a graph of Meep's development, so plotting lines of code versus the year starting in 2003, and the color codes are colored by what year the code was added. So this is from a nice tool on GitHub called Git of Theseus, referring to the famous ship of Theseus of philosophy. So is it the same program if 90% of it has been replaced by other code? So there's still about a third or a quarter of the code from 2003 is still in the code base, and you can see a big a kink where the development goes almost vertical in 2017. And so this is thanks to Artavan, who started this company called Sympatis and got some support from NSF and others, was actually able to hire full-time Python developer who was able to add the Python interface and added and subsequently quite a bit of other stuff. There was a kind of a fallow period from 2010 to 2016 or so, where in my group, we weren't developing Meep too much because we were mainly using some other tools at that time in our group. So it kind of was on maintenance mode. And you can also see it if you look at this is a graph of the same thing, but showing the languages. And so the core of it is in C++, and the purple is C++ headers, so it's also C++ code. And then in 2017, you see a huge chunk of Python code. So now that's almost a third of the code base, more than a third of the code base, and it says, which is now almost 100,000 lines of code. So what I want to talk a little bit about today is where does Meep fit into the broader picture of electromagnetic solvers? So in electromagnetic solvers, we're trying to solve Maxwell's equations, which I've tried to write down here in a fairly complete form, but even then there's going to be some missing stuff. So there's electric field, there's magnetic field, but there's also, when you have materials, there are polarization densities in the field, electric and magnetic polarization densities, and these give you additional displacement and magnetic fields that are related to E and D and H and B and M. And you have current sources, J. Here, physically, you only have electric current sources. Mathematically, you can have magnetic current sources, which are not shown here, but Meep supports it. It's quite nice computationally to have both. And there's actually, this is not complete. There's still a lot of missing physics here because there's a complicated story of how do the polarizations, P and M, depend upon the electromagnetic fields, right? So how do which basically is a question of how the materials respond to the fields. And there's a lot of different models you can put in, many of which are supported in Meep. Probably the simplest one is just linear dispersionless materials, where P and the polarization is just proportional to the field with just a constant, epsilon -1. And so then things simplify quite a bit. So these are the time domain Maxwell's equations, where you evolve the field in time. If it's linear and dispersionless, or even if it's not dispersionless, if it's linear and time invariant, I should say, then you can Fourier transform, look for time harmonic fields, and then the time derivatives turn into factors of I omega. So these are the frequency domain Maxwell's equations. So even in this case, and this is not the most general case, it's not, Meep supports a wider variety of materials than this. It's still pretty complicated. It's kind of a messy set of PDEs. So there's a few classic cases where you can solve this. So in the limit where the wavelength is very small compared to the geometry. And of course, the solution of this are waves, electromagnetic waves, as first shown by Maxwell. So if the wavelength is very small, then you can use ray optics. You probably learned in high school, you can treat light as rays that go in straight lines. If the wavelength is very large, you can use quasi-statics or Poisson's equation. So the wave nature drops out, and famously, this is the regime where you can just use lumped circuit models, resistors, capacitors, and so forth. You don't have to worry about waves bouncing back and forth between the walls of a capacitor. It's just a quasi-static field in there. So the hard case where you need full electrodynamics is where the wavelengths are comparable in size to the geometry. And in most cases there, if you want to solve it, you need a numerical solution. So if you look at how the history of classical electromagnetic computations, it follows a similar outline to many fields. If you look in fluid dynamics or other kinds of things. In the very beginning, 100 years ago, 150 years ago, you solve as much as you can completely analytically, right? And there are only a handful of cases you can solve. You can solve for vacuum. You can solve for a planar interface. You can solve various electrostatic problems that you probably solved in freshman year of college. And then you can do some things approximately, like for example, scattering from small particles was famously solved by Lord Rayleigh. You can solve some things with periodic multilayer films. And in general, you can only handle problems that have very high symmetry and/or separable solutions and/or small parameters that you can pull out and approximate. So the next step, you run out of these pretty quickly. So the next step is you do semi-analytical solutions. You try and develop a series expansion that's usually very specialized to the geometry that you're trying to solve. So it converges extremely rapidly. So these are nowadays often called spectral methods. And the classic example of that is scattering of light by a sphere. So you're scattering light by a sphere, but it's not extremely subwavelength. So you have to expand the wave in spherical harmonics. So that we don't have to, but if you expand the wave in vector spherical harmonics, that's sort of matched to the symmetry of the sphere, to the separability of the problem. And so you can get something that, the advantage of these things, you can get things that converge extremely rapidly, can converge exponentially fast. So even in the days before computers, you could actually apply these and sum up laboriously just a few terms, and you can get a pretty good approximation for the solution. And so nowadays, I would think of these as spectral integral equation methods. So essentially, you're exactly solving the solutions in the homogeneous regions, so where inside and outside the sphere, where there are vector spherical waves, and then you just match boundary conditions at the boundary. And on the boundaries, you're expanding in some kind of spectral basis, like a Fourier series or spherical harmonics. And so these actually do generalize to arbitrary geometries, where you expand in Fourier series or Chebyshev polynomials and things like this. And the advantage of these, as I said, is they can converge exponentially fast. So they're fast enough even for hand calculation 100 years ago. And when something converges in only 1 or 2 terms or 3 terms, you can actually look at those terms and get some analytical insights and think about the asymptotics and so forth. But the limitation is that if you want this exponential convergence, you need to redesign the basis for every single geometry. So the spherical harmonics work great for spheres, but if it's an ellipsoid, then you need some more complicated series. And if you have a cube, forget it, you're in big trouble, right? And in general, so what happens is if you look at it over time, they start with a case of spheres and so forth, and then they slowly try and add bells and whistles. They design more and more complicated bases and glue them together for different shapes. And it gets messier and messier and messier as you're trying to go to more complicated geometries. And so at some point, people jump ship and they say, okay, screw it. Let's just slap a grid on this and just use a generic grid or mesh, or just where you usually use low order polynomials in each grid element. So that's that's the classic finite element method, where you have like a irregular mesh, and in each mesh element you use low order polynomials. You can discretize space this way. That's your PDE methods. And you can also discretize surfaces this way and have boundary unknowns. Those are surface integral equation methods, and that are coupled by Green's functions. And you can either just use a uniform grid and approximate derivatives by differences, or we can use arbitrary meshes and use more complicated finite element methods. And so when you do this, going from these semi-analytical solutions and spectral methods to these brute force methods, you lose orders of magnitude in performance. They're way, way slower for solving scattering off of a sphere than expanding in spherical harmonics. But you get one code that you can reuse in every geometry. And at some point, computer time becomes much cheaper than your time. However, I should say that one thing to keep in mind is that everything here is still in widespread use. So if you look at papers in photonics, probably 90% of the papers at least, use mainly brute force methods. And these are kind of the first resort if you just want to see what happens in a new geometry, if you just want to get a number. But people still use geometry-specific spectral methods. They still use Smith scattering. They still use spherical harmonics and other specialized expansions, especially if there's some particular class of geometries that's you're really interested. You want to either really scale it up to a really big system, or you want to really understand it analytically. I mean, these are really powerful, and they're much, much faster than the brute force methods. And people still use analytical techniques. But nowadays, you're using analytical techniques less just to get a number out of things, less to find out what happens, and more to try and see something more general. For example, to prove theorems like upper bounds on what can happen, or conservation laws and things like that, or to treat small perturbations, because computers are very, very bad when there's a huge discrepancy in scales, when there's something that's really big and something that's really small, or something that's really fast and something that's really slow. Then if you're trying to slap a grid on it, then you have to get a grid that captures both things at the same time. But that's exactly the case where you can use analytical methods to try and tease apart those scales, using, for example, perturbation theory. Even with numerics, even with brute force numerics, there is no single winner, no single best algorithm. So there's lots of methods that continue to be in widespread use. So they all have their strengths and weaknesses. So there's trade-offs between simplicity of the method and generalizability of the method and its performance or scalability, for example. When you have very, very mature and standardized problems where everyone is solving exactly the same thing, like you have an integrated circuit and you're trying to extract the capacitance or mutual inductance of different elements in the circuit, and it's always the same problem for many, many years in a row, then people migrate to very, very sophisticated, very specialized methods, like very fast surface integral equation methods. And whereas in research fields, people tend to use simpler methods, like FTTD, for example, that are really easy to modify and generalize. So if you look at the different computational methods, it's useful there's a lot of them out there, and it's useful to try and divide them along different categories. And so there's sort of three orthogonal axes you can divide computational methods among. So you can divide them among what problem is solved. Are they solving, for example, an eigenproblem, trying to find the harmonic modes? So it's setting the currents, the sources to zero, and finding the resonances, right, or the modes. Are they trying to find the frequency domain response? So you put in a time harmonic current, you're trying to find the time harmonic field. Are they trying to find the time domain response? You put in a time-dependent current, you're trying to find the full time-dependent fields. Are you solving the PDE equation or the integral equation? You flip things around in terms of Green's functions. And once you've decided what problem you're solving, what equations you need to discretize it on the computer. You need to reduce your infinitely many unknowns, the fields at every point in space, to finitely many unknowns. And there are many ways to do that. You can use finite differences. You can use finite elements or boundary elements. You can use spectral bases or Fourier bases. And there are other techniques. People even use neural networks these days to try and represent the unknowns in what are called pins. And once you've discretized the unknowns, then you have some big problem, and now not infinitely many unknowns, but maybe a million unknowns, and now you need to solve that. And so then there's a lot of different solution methods you can apply. You can apply, often these things turn into problems in linear algebra. So you can talk about dense matrices, dense linear algebra. You can talk about sparse matrices, sparse linear algebra, or even other fancier representations like fast multiple methods or sort of approximate low-rank factorizations of matrices. You can solve them with direct methods. You can solve them with iterative methods. And if you're evolving in time, there are a whole zoo of ways to evolve things in time. So Meep is choosing basically the most general possible problem out of these, the time domain response from the time domain currents, and the simplest possible discretization, just slapping a uniform grid on it, and using finite differences, and a uniform grid in time, and using what's called explicit time stepping, where each new time step is just mathematically, it's just a sparse matrix times the old time step. And so this is, of course, the finite difference time domain method, or FDTD, which was introduced by Yi back in 1966. It actually didn't really become widespread until the 1980s. You really need compute cycles to spare before you just start slapping a grid on things and evolving them in time. And the advantages of the FTDD method are first extensibility, because it's so simple. It's just the simplest possible discretization. It's relatively easy to add stuff into it. So if you want to add complicated materials like lasing or chiral materials or time-varying materials or time-varying sources, any weird boundary conditions and so forth, you can slap those in relatively easily. Whereas if you have a much more sophisticated method, for example, boundary element methods, every change to the materials can be almost a research problem sometimes. So it's also extremely general because it's the full time domain Maxwell's equations. That means it can basically model any electromagnetic phenomena as long as you're willing to implement the material model for that. Including, you can do the other problems too as well. You can solve frequency domain problems with time domain by sticking in a pulse and Fourier transforming the response to that, for example. But you can also handle things that you can't do in frequency domain because they're not linear time invariant. For example, you have strong nonlinear effects like in lasing, or you could have time varying problems where you have actually materials moving around in time. It can be handled in a full time domain solver like this. It's also very nice if you're interested in broadband problems because you're simulating in time. You can solve for many frequencies in a single simulation. You can hit it with a pulse that's broadband, and you Fourier transform the response, and you get lots of frequencies in one shot. As opposed to frequency domain methods, which typically have a separate linear solve for each frequency. And there are some techniques to try and share computations between those, but really fully exploiting that is still a research problem. It's also scalable in the sense that it's straightforward to parallelize this. You just chop your grid into pieces, and then they only communicate between the different processors in the boundaries between each piece. And we've done some work on adaptive load balancing and other things to try and make that scale even better. It's also uniform. There's no mesh generation step. You don't have to worry about where your triangles go. There's just one grid with one resolution. So you specify one number, which is the resolution, and you crank that up until it converges. So that makes it relatively simple to use and to put in. You can put in objects anywhere you want, and it doesn't change the grid. That's also a disadvantage, right? So the uniform resolution also means that if you have some regions where you need much more spatial resolution than others, then these are going to be much more difficult to handle. So the classic case of this is plasmonic materials. So if you have a plasmonic response and you're really trying to resolve the fields inside a metal as well as outside, so like metals at optical frequencies, and then inside the metal, the length scale of the field, the skin depth can be orders of magnitude smaller than the length scale of the field in the air. And so if you're trying to have one uniform mesh that captures both, you need a pretty fine mesh. It can be done if you have enough cycles. Meep can handle this, but it's not the most efficient way to do things like this. Now, there are extensions of FTTD to non-uniform grids, although not in Meep currently. But even those are not as flexible as finite element methods, where you can just have an arbitrary unstructured mesh and conform it to the boundaries and gradually change the resolution or rapidly change the resolution and so forth. And there'll be a talk later today by Kurt Busch on how you apply still time domain methods. You still retain that full generality, but with finite element and arbitrary meshes. And so they're developing a nice package for that. Another issue is that even if you have a non-uniform mesh, if you're doing explicit time stepping, so technically the time step has to be proportional to the spatial resolution. So if you need an extremely small spatial resolution in some region of space, then you also need extremely small time steps for stability. And there are ways around that. You mix implicit and explicit time steps, but they start making things more complicated. And then as methods become more complicated, it's harder to put in complicated materials and other things you might want to do. There also, of course, FTTD is, I would say it's slower, than very specialized solvers in many cases. So if you really just want to solve eigenproblems, right, there are specialized eigensolvers that are going to be faster than trying to solve resonant modes in Meep probably. If you have specialized types of geometries that your solver can exploit and FTTD does not, you can do better, especially since FTTD is usually low order accuracy. It's certainly not going to get the exponential accuracy of spectral methods, for example. But even with finite element methods, you can potentially use high order accuracy more easily than you can in finite difference time domain. You can support very general material models, but the simplest, most common thing is just a linear material that has dispersion that's frequency dependent. So at every frequency, there's a different dielectric constant. And if you have a frequency domain method, if whatever frequency you have, you just plug in that number for the dielectric constants. It's easy as pie. In a time domain method, we're evolving things in time. We can't just plug in things as a function of frequency. So you have to map that frequency dependent material response into some causal model of the material. So the material, you describe it by a series of, say, Lorentz-Strudel models, like Lorentzian resonances, which is basically just damped harmonic oscillators, and you fit that to your dispersion. And the more complicated of the material dispersion, the more complicated the material frequency dependence is, the more expensive that model becomes. So it starts to become expensive and a little bit awkward because it requires fitting. It's also more complicated than to use than if something that just does one thing. If you just want to solve eigenproblems, then every FTTD simulation is really a full numerical experiment. You have lots of parameters to set up. You have to set up currents as a function of time. It's like constructing an experiment, whereas something that just solves for just one thing, like just eigenproblems, you just say, here's my structure, give me the eigenvalues. You don't have to think as much. So, as far as where Meep is going, there's lots of improvements that are possible. For example, to performance, there's lots of low-hanging fruit in terms of performance, but also in terms of features and issues. If you look at the GitHub and look for any issues that are marked enhancement, those are things we'd like to add, or we'd like to have someone add in the future. So there's lots of room if you want to jump in and help, or if you have another idea that's not there, feel free to file an issue if you think there's a useful enhancement. As far as performance goes, there's lots of little things you can do, and if you do little things one after another, 20% here and 20% there eventually adds up. But I think the most useful way to get performance improvements is to think out of the box. And often if you look at your problem, there are non-obvious transformations that can take into problems that are seemingly intractable and make them tractable. You have to remember that even though this is a numerical experiment, we're not constrained to do things that you would do in a physical experiment. You can put in sources and materials that are not physical. You can measure the fields anywhere in space. You can do lots of things that would be impractical in an experiment. And this allows you to get huge benefits. So the classic example is adjoint differentiation. If you want the sensitivity to 10 million parameters, you can do it with one single simulation, as long as you can measure the field everywhere where those parameters are. There's clever reformulations of optimization problems, for example, to find resonances that allow you to do things much more efficiently, or there's tricks from complex analysis to look at averages over lots of frequencies at once, or other kinds of things. There's tricks from reciprocity, for example, to transform emission problems into absorption problems that can save you orders of magnitude in the number of simulations. So definitely it's worth thinking creatively if you have a problem that looks like it's going to require huge supercomputers to solve. And my final tip would be, as a theorist, as I said, there is no single tool that's a panacea. I'm not going to come here and say Meep is the best tool for electromagnetism. This is the only one you should be using. You should have many tools in your toolbox. And in our group, we use Meep, we use FTTD, but we use lots of other things. We regularly use finite difference frequency domain methods. We regularly use finite difference finite element methods, RCWA especially for periodic surfaces, boundary element methods, plane wave expansions, for example, on MPB, and custom methods. For example, you might do semi-analytically or approximately try and combine several methods together and stitch them together in a way that's much faster than any, and more powerful than any individual piece. And also, I know there are lots of commercial tools out there. There's Lumerical, for example, FTTD and RSoft, and I don't know, HFSS and Ansoft and ComSol. And these are all, powerful tools. But I have always tended to gravitate towards free and open source tools. Commercial proprietary tools are great, but they tend to be optimized for solving really well-established problems, for solving the same problems that everybody else is solving. And if you want to be solving new things, you don't want to be constrained by the design choices that are made by somebody else in some package that you can't get into and modify. So I'm going to stop there. So the next talk, which is in 15 minutes, is going to be by Alec Hammond on topology optimization in Meep, and then we'll have a break and a whole series of exciting talks after that. But let me stop and thank you and ask for if there are any questions.
Thanks, Stephen. That was really, really nice to see the history. Can you say something about what your methodology is for verifying all of these complex tools? I suspect that maybe there's a hierarchy of how you validate things, how you ensure that you're correct to a certain degree. We saw yesterday that built-in things such as energy conservation is one way, but I'm thinking specifically about lower level, looking at analytic solutions and doing comparisons. And do you think that's just an intrinsic part of what you do, even though it wasn't elaborated on just now?
Yeah, so definitely when you're developing numerical solvers, you need to validate them. You need to make sure they're correct, and you need to make sure that they're converging, and they're converging at the expected rate, right? So if often source of bugs is things converge, but converge more slowly than they're supposed to, or an indication of bugs. And so, here you're solving, the whole purpose of the tool is to solve things you can't solve by hand. So then how do you check it? So of course you can check, general properties like conservation laws and other things that the first thing you do is you just run it and see if it looks right? Because it usually, initially, your first pass isn't working at all, and so the solutions blow up or they do something crazy that isn't right. So once once the solutions are looking more or less right, so then what else you do? So you can check it against the analytical solutions. There are analytical solutions in a handful of cases, and so that's really useful to check against, especially when you're first starting your first tool, and the nice thing about computers is that a method like FTTD is not very specific to the geometry. There's nothing in Meep that knows that you're simulating a sphere versus a cube, except for the distribution of dielectric constants. So if it gives the correct results for a sphere, it's pretty likely to give the correct results for a cube. That being said, you also you want to test it for other things, and so then you test it against other tools. So if there are 2 or 3 programs that agree on a geometry, then that's a good sign that they're working, right? Or if it just matches something that's really well established, that's been around and been validated, itself validated against other tools. So for example, when I had this eigensolver MPB, which of course we validated for analytical cases like multi-layer films and a few cases where you have analytical waveguide solutions, but we also validated against other codes that we had in our group, and then and eventually was validated against experiments as well. Although you can't do very high precision validation that way. And so the MPB, by the time Meep came around, was extremely well validated. So then if you put in Meep and you put in a periodic boundary conditions and you look for the resonant modes, then it should match MPB to high precision. And then that's a good way to check with how we check the convergence rate and the accuracy of cyclical smoothing is we could take MPB and we could crank it to really, really high resolution to get a really accurate solution. And then we'd see how fast Meep converged to that. And as the physics becomes more and more complicated, validation becomes more and more difficult. One of the trickiest things to validate in recent years was laser modeling, in which you couple Maxwell's equations to a set of nonlinear rate equations for basically describing the gain medium and how many excited states you have there, called the Maxwell block equations. And so these are really complicated nonlinear time-dependent PDEs. You don't easily have any analytical solutions except in extreme limiting cases. And they're nonlinear, so that means they're extremely everything can be implemented correctly, but if it won't match another code if the units are different or some scaling is different, right? And it won't even match it qualitatively; it'll just be completely off. So that Alex Surjan did a lot of work there on validating against earlier solvers that he had also Maxwell block solvers, which themselves were validated against other solvers and validated against, there's a technique called a different numerical technique called SALT that solves for the steady state directly and was validated against that. And so you have to have this whole hierarchy of tests. So the linear materials are a bit easier to validate. So for example, if you just put in a single point unit cell that's only 1 pixel of periodic boundary conditions, it's just a uniform medium, then you can replicate just the analytical dispersion relation of that structure, and then there's a bunch of other tests. So, but yeah, you have to do all of these things to test it. But and one of the disciplines we've tried to adhere to that is a pain at times is every time you add a new feature, you add a test, so that the test suite grows slowly over time, and every time you add a new feature, you run all the tests to make sure you didn't accidentally break something else.